Hey everyone, welcome back to Math 251. In this video, we are going to talk about discontinuity. So far in this class, we have been talking about what it means for a function to be continuous, but we haven't really gotten onto this topic of what it means for a function to be discontinuous. And that's what we're talking about today. So we have three different ways that a function can be discontinuous at a certain point. The first one is called a removable discontinuity. And this basically means that the limit of our function as we approach this a value exists. So the limit of the function as we approach the point where we have this removable discontinuity exists. However, the function is defined where the limit is not. So this picture is a great example of our limit exists, right? Our limit would be this guy right here, but our function is defined somewhere else. We know that a function has a removable discontinuity if we can basically just like fill in a point and then it's continuous. So I can just fill in that one single point and then my function is continuous. The second kind of discontinuity we can have is called a jump discontinuity, which is exactly what it sounds like. Basically, we are on one piece and then we jump to another piece. And it's worth noting here that the limit as x approaches a of a function like this does not exist, because the limit as x approaches a from the left and the limit as x approaches a from the right are two different numbers. Because the limit from the left and the right are different, that means that this limit does not exist as x approaches a of this function. So this is a jump discontinuity. And then finally, the last kind of discontinuity we have is the infinite discontinuity, which means that as x approaches our a value, we either go up to positive infinity or down to negative infinity. In either case, either positive or negative infinity, the limit as x approaches a does not exist since we go to infinity or negative infinity. And it's important to note with infinite discontinuities that this always correlates to a vertical asymptote. We will always have a vertical asymptote when our function has an infinite discontinuity. So let's look at two kinds of functions here. We have f of x equals 2x divided by x minus 2 squared, and g of x is a piecewise defined function as x squared plus 1 for x less than 2, and 3x for x greater than or equal to 2. What kind of discontinuities do f of x and g of x have at x equals 2? And what does this mean about the limits as x goes to 2 of f of x and g of x? All right, so we basically want to see which one of these discontinuities these two functions have. If I were to graph f of x, this is what it looks like. Here is f of x. And we can see that we have a vertical asymptote at x equals 2. Right? And we know that we have this vertical asymptote because if we set our denominator equal to 0, which is what occurs when we have a vertical asymptote, we get x equals 2. So no matter how far out we zoom, we see that our function will go up to positive infinity on either side of x equals 2, which means that this is an infinite discontinuity and that we have a vertical asymptote at x equals 2. So for f of x, we have an infinite discontinuity at x equals 2. Continuity at x equals 2, which also means that we have a vertical asymptote. I'm going to abbreviate that as VA, vertical asymptote at x equals 2. Okay, what does this mean about the limit as x goes to 2 of f of x? Well, since our limit is plus or minus infinity, in this case plus infinity, on either side of x equals 2, this limit does not exist. So we'll write the limit as x approaches 2 of our function does not exist. All right, what about g of x? G of x is a piecewise defined function. If we were to graph this, let's see, the piece that I care about is x equals 2. The point that I care about is x equals 2. So if I'm less than x equals 2, my function is x squared plus 1, which will look something like this. And then I have an open circle here. And then after x equals 2, I have the function 3x, which would be something like this. So what's going on here at the point x equals 2? Well, on the left-hand side, this is the y value of 5. This is the point 2, 5. If I were to plug in x equals 2 into x squared plus 1. And then on the other piece, this is 2, 6. If I plug in 2 into the function 3x. We can see that this function jumps at x equals 2. It jumps from the y value of 5 to the y value of 6. That means that we have a jump discontinuity at x equals 2. So g of x has a jump discontinuity at x equals 2. And when we have a jump discontinuity, that means that the limit as x goes to 2 of this function does not exist. So the limit as x goes to 2 of g of x does not exist. But we do have separate right and left-sided limits at x equals 2, right? So the limit as x approaches 2 from the left of g of x, well, we would be on the quadratic piece, which has a limit of 5. And the limit as x approaches 2 from the right of this function, that means we're on the linear piece, which means that this function is equal to 6. So these two one-sided limits do exist, but since they are not the same number, our overall limit does not exist. All right, that is it for this video. I'll see you next time.